Good afternoon, good morning everybody, or depending on the location in the world where you are. We'd like to start in a few seconds with our webinar on pipeline modeling, pipeline hydraulics in WANDA, what's new in WANDA 4.2. And if I'm right, everybody can see now my screen. I would like you first to welcome you to this webinar and thank you for taking the time to join us. If during the webinar you have any questions, you can raise your hand, or there's a question dialog where you can ask questions, and my colleague Michiel Tucker is also joining us, and he'll try to answer your questions during the webinar. At the end of the webinar, there will be a short Q&A session for any questions which will be remaining. During the webinar, during the topics I will be discussing, I will also see if I can already answer some questions which are raised based on the topics which we are busy with. Today I would like to talk about the following items which are included in the new WANDA 4.2 release. The first is the new user interface, iGraphics 2013. Second is the vent with automated level effect and weir functionality, which will become clear when I'm discussing this topic. Then there's a new fast filling pipe. I want to talk about the parameter script. And at the end I want to talk about some new heat components which will be included. And I want to talk about the four-way heat exchanger and the rigid column pipe with a grid for the temperature. But let us start with iGraphics 2013. At the moment we are still using iGraphics 2007, but to improve the compatibility with Windows 7 and also Windows 8, we want to move to the newest version of iGraphics. And this also will result in an updated look and feel to modern user interfaces. And one thing which I find attractive of the new iGraphics 2030 is the extended recent file list, which I will be showing you in a minute. I will now start WANDA, so you can see how it looks. And one thing to notice, in the taskbar you see here the icon is changed. It's not longer the colored icon, it's just a more simple icon, but that's good to know. Now the shape palette is just the same, where all the shapes are, and also the tabs for the different domains like control or heat or normal liquid. And as I said, we have here now a recent file list, which is much more extended than the four which are in the iGraphics 2007. So this makes it easier to keep track of models which you recently opened. And I already have used it quite often to find my models back. Let's jump back to the PowerPoint. So I want to start with discussing now some components. And we start with the air vent. If you have a pipeline and you have some local high points, air can be trapped there during filling, or if the air is let in during a full pump trip, this air needs to be released. And this is where the vent can be used. Basically what you do, you start the pumps and then there's a certain discharge coming into your pipeline, and this will raise the water level first on the upstream leg of your local high point up to this point. At that moment this will function as a weir, and at that moment the second leg, the downstream leg, will be filled, as you can see in this small demo. And then if this is also at the level of the weir, then the rest of the air will be expelled through the standpipe to the air valve. All these effects which you saw, so the filling of the downstream leg, the filling of the upstream leg, and the last filling, are included. Also, the level effect is automatically included based on the profile of the connecting pipelines. So you don't have to make yourself the table anymore, as is with the air vent which we have now. And of course we can show this in Wanda, so we will jump to Wanda and I will open the model. As you can see, I'm using now the recent file list because I recently opened this model. So we have here a pipeline, and we'll show you the profile. And as you can see, there's one, this is the highest point, there are some more local high points, but at this moment I assume this is completely filled, and only here in this part, if I zoom in you can see it better, some air remains, which needs to be expelled. And basically that is done by the pumps, which are modeled as a constant head reservoir, and have here a valve which is throttled to a certain flow rate. So what will happen then? I will open the movie navigator and just drag it along because it's a long play. But as you can see, the head here rises, so the water level here rises, air is being expelled up to a certain moment. Then you can see now the downstream leg is now being filled, and if I zoom in a little bit more, you can see that the head and the upstream side is just below the center line of the pipe. So that is the bottom local point, local high point. To that point it's filled. And if I then continue, you can see that the downstream leg is completely filled, and at that moment the last air is being expelled. And at a certain moment, when all air is expelled, to zoom out a little bit, you can zoom in again to make it a little bit. Then there are some pressure fluctuations coming in. If you look at the fluid levels on both sides, the green line is on the downstream side. If I drag it a little bit more down, so that's on this side, and the red line is on this side. As you can see, on the upstream side it's first filled, and then it stops. The downstream side stays constant until the rear effect comes into action, and then it's filled, and at that point it's completely filled to the rear level, and then the rest of the air is expelled. And in the end it goes very fast because of the size of the filling pipe, which is 600 millimeters, while the pipe diameter is 1600 millimeters, so 1.6 meters, so that's much bigger. And you can also see here that after all air is expelled, the pressure rises and you get pressure waves running through your pipeline up and down stream. As you can imagine, by simulating it like this, you can design what kind of filling flow rate you should need to safely fill your system. I should also mention this example is only about filling of pipelines, but you can also use it to model the draining of your pipelines. So you can also let air in. This dual inlet, it's an in-outlet type of valve. But by setting coefficients to 0, for example, for the inlet, at that moment it acts only as an outlet, and also the other way around. So if you put the outlet to 0 then, and the inlet you put a value, then it's only an inlet valve. I will take now a short moment to see if there are any questions, and then I will continue with this presentation. So since there are no questions, I will continue with the next component, which is the fast filling pipe. Just let me close this one. The fast filling pipe is used to model the fast filling of pipelines, and this can be, for example, useful for firefighting systems, which can be dry and if there's a fire, then the water, it needs to be filled very rapidly. What happens then, the waterfront will be moving vertically through the pipe, as you can see here in this animation, and it can go very fast. So now let's jump back to Wanda. Let me see. Yes, here's the model. So of course I made an example also for this one. Here we have the fast filling pipe, and in steady state it's completely filled with air, and it's now enclosed by two valves which are closed, and if one valve opens, at that moment it starts to fill from the side which the valve is first opened. So if you open this valve first, it's filled from this side, or if you open this valve first, then it's filled from this side. During the filling, it doesn't look anymore. It can only, at valves which are opened, it can only be filled from one side and not from both sides simultaneously. The air in the pipe is expelled through an air valve, which is located at the end of the pipeline. And of course, that depends on the direction which you're filling in. You can also close this, and then at that moment the air will be compressed and then expanded again, and you get a pressure waves going back and forth like that. But at this moment we just completely fill it by opening this valve. So at the beginning of my simulation, I'll show you the valve position in time. I open this valve basically very fast. Within 2 seconds it is completely opened. At that moment you can see here the length of the liquid column in time. You can see that it moves rapidly to the end. The pipe is 100 meters long, so within 70 seconds it's completely filled. So that's quite fast. If we look at the velocities at the entrance, you can see that it goes up to 10 meters and then drops out to 5 meters, so that's also a very high velocity. But at this moment the pipeline is completely filled and there is a closed valve, so the water has to stop. So that gives a huge pressure rise, and if you look at the pressure at the end of the pipe, you can see it even goes up to 50 bar, which is very high. And if you would use Joukowsky to calculate based on 5 meters per second and a wave speed of 1000 meters per second, you get exactly this pressure rise of 50 bar, which we see here. To make it more safe, what we can do is we can decrease the size of the amount of air released to decrease this. I did it in this model, and then if you look here at the length of the liquid column, you can see already that it's much slower. So it's in 30 seconds it's filled. Again, then we look at the pressure rise at the end. You can see the pressure increase is also much smaller. It goes only up to 24 bars. So that makes it already a lot better. Also, by changing the head which you put here, you can decrease the velocity in which it's filled. I should make one note to this component, that it cannot be used in series or in parallel. It's at the moment just a single component because it doesn't have any information on the amount of air which are in other fast filling pipes. This might be in future development, and especially if you're interested in this, please let us know so we can see if we can start on this. Again, I take a short moment to see if there are any questions. I will be right back. So then we are back because there are no questions at all, so we can continue with the next subject, and that is the parameter script. In the Wanda versions which you are using now, the parameter script is already included. It was developed already in Wanda 3, and the purpose of it was to make it easy to determine effective parameter variation, like the wall roughness, but also the effect of a bigger search vessel, smaller search vessel. You can use it for the design. Basically, you can change all input parameters and see what effect it has on the outputs. To make it more accessible, we're going to release an Excel tool. So then more people hopefully are going to use it. And how it is going to work is like this. You start with the WANDA user interface to build a model case, where you just put your pumps, your pipes, and your valves in it, and also, if applicable, or your control system. Then you take the Excel tool, and there, I'm going to show you later how this works. You're going to put in all information about the inputs and outputs you want, and then this tool creates a WPS file, which can be used to run the parameter script together with the model case to produce some child cases, and also an output CSV file where the outputs as specified in this phase are listed. And that can be opened in Excel, but also, for example, you can load it into MATLAB, of course, just what you like. So now we're going to show you how this will work. We have an example case. This case will also be delivered with the new WANDA release. So you can also look, if you install WANDA 4.2, you can also look at this case and see how it works. This example case is based on the sewage transient example, which is already now available. And what you have here a sewage transport line, and here you have a pumping station in a branch which also is connected to this line. And we want to look at the flow regimes that both pumping stations are operating and only this pumping station is operated. And to design or to look at the extreme pressures, we want to look at the full pump trip and also at the valve closure at the end of the line. And for the valve closure, it is interesting also to look at different closure times. So basically, this is the model case. And I'm going to open the Excel sheet. You should note that you should have macros enabled to be able to work with this. And also another note, I'm using a somewhat older version of Office, but it also works in the Office 2010. So that's compatible with that. If you look here in the Excel sheet, there are 3 sheets, and I will come to them all. The first, the cases sheet, there you define your cases. And we have here the A and B column, first columns, where we just define some data for the user, so then it's easy to distinguish between the different cases. For example, I can see here that I have a full pump tip scenario with flow scenario A. And here I have a valve closure scenario with flow scenario B and closure speed 1. Here you can just put everything what you like, you can put it in. And here we have the include column. If there's a 1, then it's included in the parameter run. If it's a 0, then it will not, it's excluded. So if you have more cases and you want only to run some cases, you can just use this column so you don't have to delete everything. Next column is the name column. In the yellow field there, the name of the model case should be stored, and this is the name of the child cases. And everything over here is input parameters. And in the top, there's the name of the component or the keyword. And below that is the input property you want to change. For example, I have here the PG1, that stands for pump group 1. It's a keyword for pump group 1. So there's pumps, I have the initial discharge, and I have the value 0 and 3000, which I'm using. I also have here for the same pump group, I have the initial setting. If you make a jump to WANDA, you select the pump, you can see here that the initial setting is a drop-down list. And if you select this drop-down list, see, and you have to put a value there. So this is 1, 2, 3, 4, 5. It just works very easily, as you would expect, of course. So if I put it to 1, it's setting on initial speed. And then WANDA will use this value, and this one is disregarded. The same as if I put it on 4, that's initial discharge. Then this one is disregarded, and we'll put the pumps on discharge of 3000 cubes per hour. Finally, you can also change control components. So that's what I'm using here to define the closure speed of the valve. And I can also disuse components. So I'm turning them off in the case. And then 0 means off and 1 means that it's on. You should note that in the mother case, all components which are listed here, so also the components which you want to disuse, should be used, should be on. Otherwise, they will not be recognized and you get an error message. So this is for the case sheet. Then we have the output sheet. There we start with what we call a save keyword. You can see here if a drop-down list which shows all available. So we have no children, then it doesn't save any child cases. We have save case, then it only saves the case. We have save message, and it saves the message files, the unsteady and steady messages. We have save all, then it saves the case and the message file. Finally, there's rebuild CSV. That's one if you have run the parameter script and you have all the child cases and you think, okay, I need this extra output. I would like to know the extreme pressure on this point. Then you can just include it in this list and rerun it with rebuild CSV. Then you don't have to run all your simulations again. For the output, it works very similar to the input. You define your name of your component or your keyword, and you put here the output property which you would like to export. And at the end, you have to specify if you want which extreme you want, or if you want the max or the min. Please note that we can only export extremes at the moment. Time series is not possible, and also at a certain time step is also not possible. The last sheet is a readme, which is just basic what I just described. So here it's just some reference for you if you're working with this Excel tool. I'm just going to get some slug of some water. Sorry. So if you filled everything in, you can press here the Create WPS button. Then you get a dialog which asks you to select the mother case. This moment, because the mother case is stored here, it opens that file. So I can just press immediately Save. And I get the message that the WPS file is created successfully and that I can run the parameter script from Wanda. And here also it's stated how this can be done. That's what we're going to show you now. So we go back to Wanda, go to Model, and then here at the bottom you can see Run Parameter Script. So if I press that, you can see then the parameter script starts to run. And there's a lot happening. Basically it performs a steady calculation, then the unsteady calculations, then makes a new child case and reruns the steady and the unsteady until all the cases are finished. So you can see it goes quite fast, and at the end the CSV file, the output file, is opened. And in the CSV file, these are all the input parameters I gave in, and this is all the output I gave in. And it's stored like as follows. For example, if you look here at this pressure column, it gives the value, so the minimum value. It gives the component where this minimum pressure occurred, and also at which time it occurred. That can be very useful in evaluation of your result. For example, if you want to design a search vessel, your minimum pressure may be not acceptable if it's negative, so then you can just put different sizes of search vessels in it and then you can see, okay, I should have this size. At the end, if you jump back to the Excel file, this column are also automatic links to the child cases. So if they are created, and I can click, for example, on case 5, and I say OK, and then the case is opened in Wanda. What I can do then, for example, I can look at time series. So based on the results in the CSV file, I can evaluate, oh, that's something strange, and I can open the child case and see, yeah, what is happening. So with that, I would like to conclude on the parameter script and jump to the next session. But before I go there, I just want to have a quick look if there are any questions, and then we will continue again. Okay, we will continue. I see there's one question, but we have to look a little bit more into that. We come back later on this question. We're now going to jump to the heat components, and we start with the four-way heat exchanger. This is basically a sketch of how it works. You have a stream of hot water and a stream of cold water, and in the heat exchanger the heat is transported from the hot side to the cold side, so the temperature rises on the cold side and the temperature decreases on the hot side. It's basically, very simple. And of course we have an example case of this. It's a 4-node component, so it has 4 connection points, and I put here the numbering of the connection points, and the flow goes from T1 to T2, that's positive flow, and from T3 to T4, that's also positive flow. And then basically it's working in countercurrent flow. But you can also operate it in co-current flow, and you can also change the direction of heat transfer. That's completely independent of for the design. It works all directions. So what you can see here, I have here a hot stream of 100 degrees Celsius, and it decreases to about 90 degrees Celsius. Here I have the cold stream, which starts at 40 degrees Celsius and ends at approximately 51 degrees Celsius. So the heat transport is transported from this side to the other side. What I will do then is I will decrease the pressure in this P3 bound. I drop it down to 8 bars. The initial pressure on the other side is 9 bars, so the flow will reverse in direction. And next to that, I specified here that the constant temperature is 20 degrees. So if this PT bound starts to supply water, it will supply water with a temperature of 20 degrees Celsius. So if you're going to look at the temperature here, the time series, you see it starts to drop because the flow rate will decrease. At a certain moment the flow is reversing, and then at that moment it starts to supply water with 20 degrees, and then it's constant. We then look at the other side, the temperature. You see it's first supplying at 100 degrees Celsius, and at that moment the flow reverses and it's not supplying but receiving, and then you can see it receives water which is about 25 degrees Celsius, and it decreases a little because the flow is still increasing, and then it stays constant. If we then look at the other side, you can see here it starts at 40, so it starts by supplying heat from T3, T4 side to the T1, T2 side. But if the T4 becomes 20 degrees, then the heat transport direction is changed. And if we look at the heat supplied, you can also see this. You can see that it's negative. Then when the flow reverses and the other temperature comes in, then it becomes positive, so it reverses direction. So as I said, you can basically use this component in all directions if you would like. I showed you just that there's a jump in temperature here. this jump in temperature, you can make that a little bit more smooth by applying some slowness in the model by introducing pipes. And that's the next subject I would like to talk to you about. That's the rigid column pipe with a grid for the temperature. Let me just get another sip of water. At the moment we have a rigid column pipe which does not have an internal calculation grid. You only have the black points, the connection points. So basically if the temperature rises here, the temperature rises on this side, then some instance later, some time step later, the temperature starts to rise on this side already. Which is of course not very realistic unless you make your pipes really small. So by introducing a grid you can make this temperature changes in your pipe. You can model that better. You can make longer pipes. And I will show you that how that looks like. We have here our rigid column pipe. Calculation mode is rigid column. And as extra input you will see in the WANDA 4.2 release, you will see the advection velocity. And that should be in the order of the velocity in your pipeline. In this example, I modeled it in such a way that the velocity is about approximately, flow velocity is about 1 meters per second. And at the beginning of the simulation, I slowly, in 200 seconds, I raise the temperature at the beginning of the pipe. So we're going to look at the profile of the temperature. Open the navigator. I'm just going to drag it through because otherwise it's a very slow process. So you can see here, the temperature front moving through the pipeline to the end. If I'm going to look at the temperature at the beginning and the end, you can see I raise it at 0 seconds, and after about 1000 seconds it starts to increase, and after about 1200 seconds, when this one is its maximum, at the end also the temperature is almost at its maximum. That's because of the velocity of 1 meter per second. I have also an example where I only have 2 connection points. You can see why this is a useful development. Let me close it just. This is just the same rigid column pipe. I only increase the advection velocity so that I have a lot less points. I only have 1 element, so I only have outputs on the connection points. If we would look then at the 2 time series, you can see, I basically see that I make one mistake. The velocity is a lot smaller, so let's put here 1 extra 0. So I'm just going to recalculate this. So now what you can see happening, the green line is the temperature at the outflow, and that already starts to increase after about 200 seconds. Well, at that moment the temperature cannot be there yet, so this is not very realistic. So that's why you will be needing this grid, or you need to divide your pipe in smaller pipes. So by using this, implementing this in temperature grid, you can simplify your models. And the use of the rigid column model in situations where there are temperature changes is also valid because the change of temperatures are relatively slow compared to the changes in pressures. So in that case, the rigid column model can be applied for the pressure changes. So that was the last new component I want to show to you. Now we have a short Q&A session. We will just be looking at the questions and come back to you in a couple of minutes to answer them. Sorry, I'm back here. Before I forget, we have a short poll which I'm going to now to launch. and I hope you can answer those questions for us. Okay, there we are back again. Thank you for answering our questions. And I'm going to look at the questions which we have received. I have here, sorry, there's a question about the modeling of tube rupture. Basically, that's not included in this model. That's something special, a special case to model. And basically, probably you can trick this because from what I know, you have a high pressure system and the tube ruptures, and then a very high pressure is exposed to the lower pressure system on the other side. And there are some tricks to model that, but we don't have any experience with that, but we would be happy to discuss this further. I have here a question about the temperature modeling. Why you want to go with rigid column model instead of with the Waterhammer model? That's because of the calculation times. If you would use the Waterhammer model and you would make your grid really small and you use the appropriate wave speed, then you need to decrease your simulation time a lot. And I will look, I think I have an example of that. Oh no, sorry, this is the wrong example. I don't have the example. But basically, what you need to do, you need to decrease your simulation time a lot, and what will your time step, and that increases your simulation time, of course, a lot. And so, and that's basically not something you want. And also, in most cases, where there are temperature changes, the pressure change, the temperature changes are very slow compared to the pressure changes. So if you have a system where there are rapid pressure changes, it's safe to assume that your temperature will not change much. I hope this answers your question. Just looking if there are any other questions, but then I would like to thank you for your attention. So we will be here for a short while. If you have any questions, you can just ask them and we will answer them via the chat. And again, I would thank you for your attention, and we hope to meet you in future again for another webinar. Goodbye.